Good afternoon. This is David Eastwood, Geotech Engineering and Testing. Welcome to our program today for design and construction of parking lots. Let's see. Geotechnical consideration and design and construction of at-grade concrete, asphalt, and gravel parking lots. I work for Geotech Engineering and Testing. We've been around for about 40 years. We do geotechnical, environmental materials, and geoforensic. We've got a staff of 60 people. We work all over Texas, Louisiana, Oklahoma, New Mexico, and Arizona. We got our own rigs, a lab, and all that. We're an accredited firm. We got about 140 people that RSVP'd, and a lot of civil engineers, a lot of people from different cities, a lot of site development engineers, a lot of civil engineers, architects. This is my contact information if you need to reach me. My email is de@geotecheng.com. If you have any questions, type it in the chat or Q&A, and I'll respond. This program is going to be on YouTube, so you can go back and watch it. There's a lot of information, so you're not going to get it all in one session. So you can go ahead, watch it on YouTube. You get other people in your company to watch it. I use these programs that I have that are on my YouTube channel to train a lot of young engineers. So a lot of these programs on YouTube are good for training for young engineers if you have on your staff to watch a lot of those. Commercial parking lots. And you can go around Houston and Texas and you can see all kinds of concrete parking lots or asphalt parking lots, Buc-ee's, Walmart. Commercially, let's see, more Buc-ee's there. Commercially heavily loaded concrete parking lots. Excuse me. I see some of the stuff for Metro here. They got their buses and they're heavily loaded. You go see some of these commercial developments. They got tail wall buildings where you have these heavy duty parking lots for 18 wheelers. Commercial asphalt parking lots. Again, Walmart, for some reason, they love to use asphalt on their parking. Sam's Club and then NRG Houston, their parking lot is asphalt. This is Rice University Stadium, and they got asphalt parking lot. This is more parking lots for the fast parking they're near the airport. Commercial heavily loaded asphalt. This is the City Houston facility out there near 59 North and 610 on the east side. They got all these heavily loaded trucks, asphalt paving. These are garbage trucks. Schools, of course. A lot of these schools, they have buses on asphalt parking. Gravel. You go out there and look at some of these industrial facilities. They got gravel parking lots and lay down areas. Industrial facility with gravel parking lots. So field exploration, whenever somebody wants to do a parking lots, we go out there and do borings out there, see what kind of soils we have before we design the parking lot. This is a truck mounted rig. We get out there and do some borings. Get sampling usually to a depth of 10 feet. get soil samples and test them. These are asphalt parking lots, truck rig, gravel parking lots, doing borings out there, see what kind of soils we have. We get our soil samples with a Shelby tube sample. These are 3-inch diameter hollow tubes. They're hydraulically pushed into the soil and get soil samples. What the soil samples look like when they come out. We look for root fibers. That tells you the depth of active zone. Uh, Roots grow to an area where there's oxygen and water. When there's not, they stop. That kind of indicates the depth of active zone. Like in Houston, we got some areas with active zone depths of about 25 feet. But as I'll describe, there's another thing that's called movement active zone, and there is active zone. But anyway, root fibers tell us what active zone depth is. These are the root fibers. As they get deeper, become smaller. In sandy soils, like in Katy, for example, where you have a lot of sand, get your sampling with a standard penetration test. That's a 140-pound hammer, drop 30 inches. You drive it into the sand, and you get blow counts. You drive it in 18 inches, 6-inch, 6-inch, and 6-inch. ASTM 1586, 140-pound hammer, drop 30 inches. These are some samples of the sand. It's called split spoon sampler. You split open, so it's samples of the sand. So if you get blow counts 0 to 4, you got very loose sands. Blow counts of 5 to 10 is loose. Medium dense 11 to 30. Most of the soils in the Houston area where you have sandy soils, the blow counts are between very loose to loose. You hardly ever see high blow counts near the surface. Logging, we take that soil samples, we cut the ends, put it in foil, give it job number, put it in the plastic bags, put it in a wax box, keep the moisture constant. You want to test these soils within 14 days. You try to measure the water level. Of course, 10 feet, it's hard to measure any kind of water level. Water table usually below 10 feet, and water table fluctuates seasonally. So the most of the water levels you get in geotechnical reports are not accurate. So best way is to check it right before construction or put a piezometer in the ground. The way you measure water table, you got a tape measure with a weight on it. You throw it in the hole. When it goes plumb, that's water level. Like I said, in most Texas, unless you're in Galveston, it's very hard to kind of measure water levels. The most of the time, it's below 10 feet anyway. Unless you got what's called perch water table, which we're going to talk about in a little bit. This is a weight on the end of the tape. You throw it in the hole, and you measure the water table. Perch water table is when you have sandy soils over clay, like if you're out there along 290 or 249, Cypress Wood area, Katy area, Woodlands. These areas, they got very sandy soils. Below that is clay. Water, when it rains, water sits in the sand and saturates it. It cannot penetrate the clay. It's called perch water table. Water just sits there on top of the clay. And you dig a hole within a foot, it gets filled up with water. Number of borings, typically we space borings for paving for parking lots, but every 100-foot spacing, about 10-foot deep. Laboratory testing, we do lab tests. This is a liquid limit test. This test, we take soil sample, we put it in this cup here, and add water to it. And when it becomes kind of liquid, we take it and put it in this cup, cut a groove through it with this and spatula, and we'll turn the handle 20 times to 30 times. When it all comes together, you get a sample of it. You put it and get the weight of it. You see how much that weighs, that sample that's wet weighs. You put it in the oven and dry it up and get the dry weight of it. The difference between the wet weight and the dry weight is how much water is in the soil. It's called liquid limit. We also do plastic limit test. This test, we take the soil sample, roll it to 1/8 of an inch. You want to know how much water is in the soil for it to behave semi-plastic. You get the wet weight of it. You put it in the oven and dry it up and get the dry weight of it. So we find out how much water is in the soil. That's semi-plastic. The difference between liquid and limit and plastic limit, when you subtract them from each other, is called plasticity index. It's called PPI. If your PI is less than 20, you got low swell potential. Between 20 and 30, you got moderately expansive. 30 to 40 is highly expansive. Above 40 is very high. Hand penetrometer and torr vane to get the strength of the soil. In a hand penetrometer, you take that, push it at the end of the sample, you read the strength here. It's a torr vane, you put it at the end of the sample, ensure the torsion. You see what kind of a strength it has. Unconfined compression, trying to find out what kind of a strength the soil has. You put it in this machine and you load it up. And this is the proving ring, this deflection. You shear the soil to see how strong it is. Use that for your pavement design. Okay. Gradation, we want to know what kind of gradation you got in your soil. Is it sand, clay, silt, gravel? You got these silts, you put some material through it, you shake it. This is a typical sieve analysis. This thing is percent pass number 200 sieve. It's 65% is sandy lean clay. Here's another one in here. You can see number 200 passing is only 20% passing. And it's mostly gravel and coarse aggregate, most like base material. Compaction, you're gonna have to compact all your soils for your subgrade, for your pavements. 95% standard Proctor density. If this is your natural soils, this is your fill. So sometimes you have to import fill. You get a 50-pound bucket of sample of the clay. This is a 50-pound of your select fill if you need it, or structural fill. If you want to use select fill, that's the soil with liquid limit less than 40, PI between 12 and 20, minimum of 50%, pass number 200 sieve. That's select fill. You don't need it. All you need is a structural fill. If you need to get any kind of a fill, you go to a pit. Pit's got different type of soils. You can have sandy areas here, clayey areas over here. So the soils may not be uniform. You get a backhoe against your soil. This is a good sandy clay. Put it in the back of the truck and take it to the job site. Load up the truck. You run a Proctor test in the lab. You bring your sample in from your subgrade, chop it to pieces, add water to it, a different moisture contents, and you compact it in this mold here. It's a 4-inch mold. You compact the soil in 3 layers. It's a 5.5-pound hammer, drop 12 inches. Called standard Proctor. 5.5-pound hammer, drop 12 inches. 25 blows per lift, and you got 3 lifts. That's the machine that does it. You get the sample, you know the volume of it. After it's compacted, you take it out and you weigh it. So you know the volume and you know the weight, you know the density. So you run these tests at different moisture contents and you will plot it. At 7%, your density is 105 PCF. At 11, your density is about 122 pounds per cubic foot. At 15%, your density is 110 pounds per cubic foot. So this is the highest. So it's called optimum moisture and optimum density. So each soils develops this optimum moisture and density at a certain time. This is a Proctor curve. Okay, it varies for each soil. It's not uniform. On the typical projects, depending on the size of the project, you may have to run 10 Proctors if it's a big project. And if you plot the strength of the soil versus Proctor curve, you see you develop your maximum strength at optimal moisture. So you want your subgrade to be strong. So you want to compact it near the optimal moisture so that you develop the maximum strength for your subgrade. One of the parameters that we use for pavement design is CBR, or California bearing ratio, which compares the strength of your soil to a bearing of a material with bearing of well-graded crushed stone. The CBR for well-graded crushed stone is 100. So crushed stone at 0.1 inch deflection, it takes 3,000 pounds for it to have 0.1 inch deflection. At 0.2 inches, you need to have 4,500 pounds. The way you run the California bearing ratio, you get a piston, is about 1.92 inches diameter. CBR for crushed stone is 100. You soak the samples for 4 days with 1 psi, modeling the load of the pavement, and calculating, of course, your resilient modulus of 1,500 times CBR that goes into pavement design for AASHTO. So you take 5-pound hammer, drop 12 inches, or 10-pound hammer, drop 18 inches, and number of blows are 56, 25, and 10 per layer, 3 layers. This is it. This is the 10-pound hammer, compacted 6-inch mold, trying to get the CBR of the subgrade. You compact that soil, you soak it for 4 days, you measure deflection to see if it heaves up or if it settles. You put it in a machine, you got a 1.945 inch piston, and you got the load of 1 psi. That's the deflection. At 0.1 inch deflection, you got a load of about 142. At 0.2, the deflection, you got 183. So CBR at 0.1 inch is 14, at 0.2 is 12. So we design CBR for this soil is 12. We use the lower value. We got projects where they want to know what the field CBR is. Actually, the parking area soils, what kind of CBR does it have? So we do field CBR. You got a truck, rig, and jack up the piston against the rig. That's your piston, proving ring, deflection. You jack it up against the rig, you load it up and measure the deflection. At 0.1 inch and 0.2 inch, you jack it up and measure deflection and measure the field CBR. Much more accurate. Engineering analysis. The kind of soils we have in Houston area, well, in Texas, really, we got fat clay. We've got fat clay all over Texas. That's a site with fat clay. Sandy soils. We got soils, near Galveston or Katy area, out there, Bridgeland area. They all got sandy soils out there. Fairfield, it's sandy soils. We got silty material, which is the size of the silt is bigger than clay. Well, clay, the grain size, but it's smaller than sand. It's really a hard material to build anything on. It pumps real bad when it gets wet. Oh, then we have some areas where we have gravel, various sizes. So we got clay, got orange clay, go deeper, you get white clay, go deeper, you get weathered rock. You know that you get rock. It's a typical boarding log when we plot our stuff. Here you got a fill, crushed stone. Below that, you got fat clay. You got a PI of about 64. Highly expensive. You go all the way down to about here, about 8 feet. You got sand. You got water at about 8 feet. And then when you hit the sand, water comes all the way about 2 feet. The hydrostatic pressure pushes it all the way up. So, fill on especially bigger parking lots, you do mass grading, and some areas going to be fill. And You're gonna have to have cut and fill areas. You can put parking lots on top of a fill as long as that soil is properly compacted. 95% is standard Proctor density. And moisture contents typically plus and minus 2% optimum. So you can put a parking lot on top of the fill material as long as it doesn't have root organics and is properly compacted. If it's got organics, you cannot accept it. You're gonna have to take it out, organics, and do it. So every time you do, of course, parking lot development, you gotta do root raking, take out all the roots and stuff. These are the soils in Texas, and if you see the red areas are all expansive soils in Texas and Louisiana. The soils are in Texas are variable. So every time you're going to build a structure or do a parking lot, you got to do a soil test. These are the soils that can expand up to 1,500%. And you can see a major part of the United States has got expansive soils, according to Corps of Engineers. In Houston, in Texas, we got Dallas, San Antonio, Austin, Houston, Beaumont, Corpus Christi, Brownsville, part of it. We got expansive soils, Lubbock and El Paso. They got caliche, sandy type soils. So we got kind of a soils we have to deal with the highly expansive soils in the Houston area. See again, Texas and Louisiana. The red stuff is expansive soils. We also look at the geology north of Buffalo Bayou in Houston. Soils are sandy. Below this line of the Buffalo Bayou, the soils are clay gumbo. So if you go around Houston, starting near where I live, which is near Spandora, you got real sandy type soils over here. You go to Kingwood near the freeway. You got fat clays, gumbo with trees and stuff. You go near the lake, Houston, you got sandy soils. Dayton, Mount Bellevue, all those areas, they got really fat clays. Baytown, LaPorte, Pasadena, Deer Park, South Houston, Pearland, Seabrook, League City, Dickinson, Missouri City, Sugarland, New Territory, Rosenberg, all these places, they got really fat clays. You start going out there to Katy, Brookshire area, we got, real sandy soils, perch water table problems. Bridgeland, Farfield, Tomball, Woodlands, they got a lot of sandy soils. Parts of Tomball, they got some fat clays. You go to all Perryview, those areas got sandy soils near the surface. Hempstead, Waller County. South of Conroe, you got sandy soils. North of Conroe, Chambers Creek got really fat clay. Westview, Bel Air, Houston area, fat clays, bunch of trees, a lot of movement. So that's kind of the kind of soils you can expect in the Houston area. Design, one of the things you have to worry about, of course, when you do the parking lot is the PVR for your parking lot. Potential vertical rise is how much heat you can expect on your soils. If your soils are expansive at a specific location, potential vertical rise is expressed in inches. Ability of the soil material to swell and shrink. I did that for Houston. S610 loop, Beltway 8. You go south of Houston, you got all the way down here. PBRs are 5-inch, 5-6 inches in Pearland. Friendswood, 5-6 inches, 7 inches. Great Wood, 6 inches. Rosenberg, about 5-inch. Fulshire, 2 to 4 inches. Brookshire, anywhere from 1 or less than 1 to 1.5 inches. Same with the 290 corridor and 249 corridor. All these areas, Spring, you got PBRs about 1, 1.5. You go to Mount Bellevue, Pasadena, Deer Park, you got PBRs of 4 to 6 inches. So it's got different movement values at different locations. So when you do the parking lot, for example, here's an asphalt parking lot. You got the asphalt surface course. Below that, you got crushed stone. Below that, you got lime stabilized layer. And then you got the moisture active zone, which use root fibers is one of the ways to determine that. and you got the movement active zone, which is in Houston area. You got fat clays, gumbo. It's about 10 feet deep. Dallas, San Antonio, and Austin is about 12 to 15 feet deep. So here's another one here. You got a paving, asphalt, crushed stone, lime stabilized subgrade. You got the movement active zone in Houston, about 10 feet near Rice University. Moisture active zone could be about 20, 25 feet deep in those areas, especially near the trees. Here's a driveway that's got expansive soils underneath it, and you got different PVRs, and you can see how much it's moving. Oh, if you go out there to A&M and go drive some of those ranches around, and you can see the some of the ranches, the ground is heaving up. It's called Gill Guy, the Australian guy who developed it, and you can see the heave out there at a certain frequency on some of the ranches out there near A&M. Here's the state highway, well, one of the freeways that we have in Texas. You can see the soils is heaved up. This is the asphalt paving that I had to shave it to make the pavement level. But you can see how the soil has come up. This is a test pit. Here's another picture that shows the fat clay. You got the asphalt base, stabilized layer, natural soil. You can see the soil has heaved up. So if you plot the PVR versus the length of the parking lot, you can have large parking lots, different amount of movement. Here's another PVR that shows the length of a big parking lot, and you can see depending on the soils, the PVR can vary. And if you want to limit the PVR on your parking lot, maybe you want to limit it to 3 inches or 2 inches. If your PI is 40 and you want to, let's say you want to keep a PVR to 1 inch, you need to remove about 40 inches of the expansive soils. So that's kind of that tells you that. And here is we want to keep the PVR to 1 inch, 1.25 inches. The yellow is 1.25, and these are the amount of the soil that has to be removed to get the PVR down. For a typical shopping center, we don't worry about this. We let it heave as much as it can. It doesn't matter. So how to mitigate the expansive soil? If you got a high PVR soils, you can remove and replace it. You can do moisture conditioning or chemical injection. You can excavate the expansive soils, bring in structural fill, select structural fill, and compact it 95% of standard Proctor density. Or you can do moisture conditioning. You may take top 2 or 3 feet of the soil, add water to it, and compact to optimum plus 4%. That soil doesn't heave as much anymore, reduce the PVR. This is your Proctor. You compact it to optimum value plus 4%. So you'll compact it 15% moisture in this case. Compact it. You got to cover the area with sheeting. If you want to, again, reduce your PVR and movement, you can do a chemical injection. Oh, this is a clay. It's got negative charge. Water's got positive charge. You add the chemicals to it. It's called cation exchange. Inject the soil, removes the monovalent cations like sodium and potassium, and replaces them with calcium, make the soil less expansive. That's a project in Houston area out there, Sienna Plantation, where we're doing chemical injection. You do chemical injection on your roadways. That TxDOT doesn't want to have PVR of greater than 1.5 inches on the main lane, and on the feeders, I think it's limited to 2 inches. So that's how you do chemical injection to reduce your PVR. Traffic loading with a typical parking lot. Again, for a regular parking lot, you don't have to worry about chemical injection or any of this stuff. If you don't want to, if for small, parking lots, you don't have to worry about any of that stuff. If you got a big parking lot and you don't want it to have a bunch of waves in it, then you can do chemical injection and stuff like that, or moisture conditioning. Traffic loading, you have typically auto and light trucks or typical shopping center types parking lots. Um, you have bus traffic, you got to design for the traffic loading. Bus traffic, heavy truck loading, design for the concrete parking lots. You can use ACI, American Concrete Institute design. Portland Cement Association has got design. ASHTO, you got pavement design. This is the ACI, commercial parking lot design construction. It's a good document. And you look at traffic loading, soil types, CBR, concrete strength. Typically, we go design life of 20 years, although they last about 40 years. Coefficient of subgrade reaction. Traffic loading, they have design index, DI1, DI2, DI3. Light traffic. DI2 has got medium traffic. DI3 is medium traffic. And DI3 is medium heavy traffic. So this is kind of a traffic loading and relates to equivalent axle load based on ASHTO pavement design. ACI has its own traffic loading. They categorize it as A, B, C, D, E. A is car parking. B is entrance and truck service lanes. C is buses. D is heavy duty trucks. E is garbage trucks and fire lane. The way they classify the soils by ACI, they say if you got fine grained soils like silt and clay, you got low support with the coefficient of subgrade reaction of 75 to 120 PCI. If you got sand and gravel with a little bit of clay, you got medium support with K values between 130 to 170 PCI. If you have sand and gravel with no silt and clay, you got a high support value and your K value ranges about 180 to 220 PCI. Typical pavement section, if you go like a typical ASHTO based on traffic loading and design index of D1, D2, D3, B4, D5, you're going to have 5-inch concrete paving for a typical auto and light truck. If you go 6 inches, you got a little heavier traffic. 7 inches, if you got like a dump truck going out there near the garbage area, dumpster, you got to use 7-inch concrete, or 8-inch or 10 inches if you got heavy loads. If you are got a project where you got all these forklifts going back and forth in your parking drives, they're lifting, heavy stuff, then you may go to 10-inch. I've had projects we have to use 14 inches of concrete because they got heavy forklifts. These are industrial stuff in their parking lots where they pick up stuff, they pick up heavy loads, compressors and stuff like that. So, and you gotta have to subgrade got to be, typically stabilized either with lime or lime fly ash or cement, 6 to 8 inches depending on the traffic loading. ACI, depending on their traffic loading, they got a different design, kind of a little different. If your soils are weak, you got a K of 100 PCI, coefficient of subgrade reaction for traffic loading A, which is the cars. B is entrance truck services. C is buses. D is heavy duty trucks. E is garbage trucks. So they got 5.5 inches, 6.5 inches for B, 8.75 inches for C, 6.75 inches D for, like a fire trucks and stuff. It's 7.75 inches thickness. If your soils are stronger with K of 200, these thicknesses drop. If your soils are really strong, K is 300, this thicknesses are, 4.75. Of course, nobody does 4.75-inch concrete parking lot. You go to 5 inches, So Some of these, 5.75 inch, that means you're 6-inch paving. The forms that we have are set up that way. They're not set up for 5.75. So from a practical standpoint, some of these numbers don't make sense. The concrete typical string is 3,500 PSI, 28 days. In a waste dumpster area, you should have concrete at least 7 inches thick, reinforced. It should be designed so that the vehicle weights of the collection trucks are supported on the concrete while the dumpster is being lifted. Typical steel placement, but depending on the design, traffic loading D1, D2, D3, number 3 bars at 18 inches, number 4 bars at 24 inches. At D2, DI2, number 3 bars at 12 inches, or number 4 at 18 inches. DI3, number 4 bars at 18 inches, number 4 and 5, number 4 bars at 12 inches. Jointing, if you got your building here and this is your parking lot, you got your control joints and you got expansion joints. These are the expansion joints. And then you got isolation joints around the building to isolate the parking lot paving from your building. Control joints, ACI recommends control joints should be spaced minimum spacing of 30 times the thickness of the pavement for parking lot pavements. Furthermore, ACI recommends maximum control joints of 12.5 feet for 5-inch concrete and for control joints of 15 feet for 6-inch concrete or thicker pavements. Saw cut should be done within 4 to 12 hours. The depth of the saw cut should be 1/4 of the slab thickness. So here's a typical control joint. These are control joints. Control joints are intended to predetermine the locations of the cracks. It tells the concrete where to crack, caused by restrained shrinkage of the concrete and by stresses induced from warping and curling. So ACI spacing is, 5-inch concrete. You need to have your maximum control joint spacing of 10 feet. 6 inches, 12.5 feet. 6 inches or greater, 15 feet. So these are the typical values that they recommend joint spacing. Expansion joints, concrete expands and shrinks. So you put expansion joints about 80 feet apart in the parking lot. Of course, they say it's kind of optional to put expansion joints, but typical practice is to put expansion joints at 80 feet. It's a typical parking lot. You can see the expansion joints. The expansion joints should be 80 feet apart. And again, the dowel spacing at the expansion joints, depending on the traffic loading. Here's the number DI1, 5-inch diameter, 12 inches long with 5 inches embedment. DI2, 34-inch, 0.75-inch diameter, that's kind of like 0.75-inch diameter, 14-inch long with 6 inches of embedment. DI3, 7/8 diameter, 14 inches long with 6 inches of embedment. DI4 is the heavy traffic, 1-inch diameter, 14 inches of long. DI5 heavy traffic, 1/8 diameter, 16 inches long with 7-inch embedment. Construction joints, you got to pour the concrete, you got to stop somewhere. Basically, you got to put construction joints at the end of the day. They provide interface between the areas of concrete placed at different times during the project. Construction joints, when the concrete planned to be placed at different times, we recommend use of construction joints. between the paving areas. So you can have butt top joints out there with no load transfer on parking lots, like 5-inch concrete stuff, not heavy stuff. You're gonna essentially have a joint in here. You got a cut here, or you can, thicken the joint. So that's kind of typical detail for 5-inch concrete paving. But for heavy parking lots, 6-inch and above, you got to have dowels going through this thing. Isolation joints. You got to put isolation joints between your building and your parking lot. Concrete slabs should be separated from other structures of fixed objects within abutting the paved areas to offset effects of typical horizontal and vertical movement. Isolation joints are to separate the pavement from these structures such as light poles, areas, manholes, and the buildings. And you can see the building in here. You put an isolation joint there. Again, building here, you see an isolation joint for thickened pavement here. That's a typical commercial facility. The building and parking. You got an isolation joint between the wall and the paving. Typical isolation joint. It's another building. You got the isolation joint. It's isolation joint between the paving and the building. The building isolation joint. And you got a catch basin in here. You got like that. You got isolation joints and manhole. You put isolation joints around it. Of course, these are control joints here. Typical drain area. See the dowel in here in this case. The pouring the concrete there. And here's the steel placement around the manhole. And you can see a joint right there. Here's another one here. You got the joint here. Joint sealer, typically we don't put any joint sealers in your control joints, but you have to have joint sealer in your expansion joints to keep the water get into your soil and destroying your pavements. It creates pumping effect that will crack your pavements. So typical control joint, you just leave it open and the concrete cracks underneath it. But if your joint is like expansion joints get bigger, you can have, putting, have to put joint fillers in it. This one put back a rod and joint filler. This one use compression seal. Bottom line is, in all your expansion joints, you need to maintain it and have joint fillers in it. Forming in place fields, liquid sealant, hot polymerized and rubberized asphalt material, cold poured like a silicone. That's a formed in place seals. Performed sealed, neoprene compression into the joint, maintaining their position through friction. So again, a lot of times I just see put, flowable joint fillers in your in expansion joints. Concrete curing, a concrete curing compound such as type 2 membrane curing should be placed on top of the concrete when you pour it. You should have a surface drainage of typically about 2% on your pavement. You got to establish good drainage. Asphalt pavements, design, Asphalt Institute, or you can use Ashto Pavement Design. You got to know soil type, CBR, resilient modulus, typical asphalt pavements. Depending on the traffic loading, on low traffic, you need 2 inches of asphalt, 6 inches of base, 6 inches of stabilized subgrade. If you're heavy loads, You may have to have 4 inches of asphalt, 10 inches of base, 8 inches of um, stabilized subgrade. I typically do not recommend asphalt in the dumpster areas. If you want to have a asphalt parking lot, put a concrete pad out there at the dumpsters. Hot mix asphalt type D, that's what we're using on the projects. Textile item 341. Base material, use crushed concrete or crushed limestone. Textile 247 spec type A grade 1. Compact 100% modified Proctor density. At moisture content being optimum 3%. Long-term pavement design depends on performance, depends on factors. You know, the subgrade got to be nice and hard, have good drainage, 2%. Install joint sealants in all your expansion joints. Extend the curves into the treated soils for a depth of at least 4 inches to keep the migration of the moisture underneath the paving. Plus, compacted low permeability clay backfill against the exterior side of the curb and gutter. Flexible base can be crushed stone, gravel, crushed concrete, Textile 247 specs. Drainage for asphalt parking lots should be 2%. Gravel parking lots, the way you do on gravel parking lots using ASHTO, you can use National Crushed Stone Association or Geroid hand design method with geotextiles. Subgrade, what we do usually lime stabilized subgrade to clay soils, or if you don't want to stabilize the soils, you use geogrid for gravel parking lots. Geogrids do really well with gravel parking lots. Flexible base, gravel, crushed concrete, or crushed limestone that we use, and the soil data for the design. You got to know the soil type, CBR values. Design, if you don't want to use geogrid for your gravel parking lot, you stabilize your subgrade, your flexible, you put your gravel on top of it. Here's National Crushed Stone Pavement recommendation. If you know what your subgrade CBR is, in this case is 6.5 inches. You come over here, this the nomograph, this is the break line, and then you go to traffic loading. In this case, your traffic loading is D5 or D4. Designing the traffic loading of that's kind of like a heavy load. You come down here, you need about 14 inches of pavement underneath it with gravel. You can put 4 inches of gravel in there, for example. Or you can have 2 inches of asphalt, the rest of it gravel. Here's a typical design that they have. If you got a fair CBR of 6 to 9, the traffic load of DI of 4, you need 14 inches of pavement. If it's your CBR less than 5, which most of the Houston is, you got to do lime stabilized that subgrade or lime fly ash it or cement it. Okay, otherwise you cannot come up with a pavement section. You can't put pavements on natural soils parking lot without stabilization. I had a call last week. Somebody wanted to use select fill as a stabilization. You cannot use select fill as stabilization. You got to use lime fly ash, or cement. If your soils have sulfate, then you cannot use lime or cement or lime fly ash. Then you just compact it and you put concrete on top of it and just increase the pavement thickness. If you got sulfate, you're going to have sulfate heave problems. Parts of Texas, you have it. So if you're in Fort Worth or Dallas, you should always check for sulfates. Design with your geogrid. You compact that subgrade, place the geogrid, and put flexible base on top of it. These guys here, GH guy design method, they determine the thickness of the unreinforced geogrid and reinforced geogrid. Drainage, of course, should be 5% on gravel parking lots so that you get sheet flow water away from pavements. So for geogrid, again, they got the like Tensar has got a good design. You use their software. and it tells you what kind of geogrid to use, and you can really reduce your aggregate base thickness. Uh, Here's back in the old days, the construction by Romans. They're doing pavement construction. They had the inspectors over here. If you didn't get your compaction, they had these sticks that it can stick you with, spears. Clearing, you gotta, if you got a parking lot, you gotta take out the trees, you gotta take out all the roots. All the roots needs to come out. If you take a tree out and you got this area, you gotta demuck it, uh, get to this hard soil, bring in a structural fill, put it in 8-inch lifts and compact it all the way to the top. You gotta run density tests for every lift. Otherwise, your pavement's gonna fail in this area. Like here. Here. You can't just push soil into it. You gotta put it in lifts and compact it. The field that you're going to use, this is not acceptable. You cannot have organics in it. So, I'm looking around to see if I have any questions. So far, I don't have any questions, I guess. These root organics are not acceptable. You cannot put them in. Not in your field, in your mass grading, on your parking lot. All the roots needs to come out. Tree trunks needs to come out. All the organics got to be removed. Proof roll your parking lot. You get a loaded dump truck, you go on it. 25 to 50 ton TxDOT specification. You should not have any deflections here. This is not acceptable. This is not acceptable. 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 If you don't proof roll, you're going to get potholes. Proof roll is very, very important. Some people kind of disregard it and they don't do proof rolling, but I'm a big proponent of proof rolling. Everywhere in your parking lot got to be proof rolled. Of course, underneath your building too. Everywhere on your site, except for your detention pond. Compact that subgrade. You can use the steel drum roller for sandy soils, or sheep foot for clayey soils. Everything got to be nice and compact. You got to run density test. Make sure you meet the compaction requirement. 95% standard Proctor density for a typical parking lot. If you got stuff that's more than 5 foot fill, all that soil should be compact to 100% modified standard Proctor density. 100% standard Proctor density. Otherwise, you're going to get settlement of the compacted soils. So remember, after 5 feet, all the soils compacted to 100% standard Proctor density instead of 95%. You run density test. The way you run density test, you poke a hole in the ground. That's the hole. You clear the area, put your nuclear gauge in there, put your nuclear source in it. It's your nuclear source, emits gamma ray. These are detectors. If a lot of it comes over here, you got poor compaction. If some of it comes over here, then that means you got good compaction. There's correlations between what the detectors get and your density and all that. They're all correlated. You compact the soils, of course. You seal it after you compact it. You come up with sheep's foot. You seal it with a pneumatic so the water sheds off of it, sheet flow off of it. If it rains, here's the parking area. You seal it with a steel drum roller. Stabilization, typical stabilization that you have in your parking lots. If you got clayey soil, use lime, for example. PI less than 15. You got sandy soils, you got to use lime fly ash or cement. 15 to 35, you can use lime or cement. Lime fly ash. PI greater than 35, you use basically lime. Lime stabilization, you use type A lime. Type B lime slurry. Type C is quicklime. On projects that you do lime stabilization, use type B. You got to have a type B lime slurry, cure it for 24 to 72 hours. After your pulverization, you're going to have gradation. 100% should pass number 1.75 inches, 85% past 0.75 inches, 60% past number 4 sieve, compact optimum plus 3%. You scrape the ground, remove the grass and weeds, you get to design subgrade. You add lime, you do lime slurry, add water if you need to, let it hydrate, break down the clay. You cure it for 24 to 72 hours. You optimum hydration, then use the pulverizer, chop the soil. This is the gumbo clay. You lime it. That's what it looks like after. Real sandy like. Gradation, and you get a sample of the soils. Yeah, it's been pulverized, and run gradation on it. Make sure it meets gradation requirements. Compact that soil with a sheep's foot. Seal it with a pneumatic. Run density test. Make sure you got proper density. Check the depths for lime stabilization. You do depth check every 50 feet. You dig a hole, put phenolphthalein in it. It turns purple. If your stabilization is 8 inches, it should not be 10 inches. If it's 10 inches, you're not using as much lime in the soil that you're supposed to. Otherwise, your lime stabilization goes bad. So you measure the depth. It should not be more than 8 inches if the design is 8 inches. Measure depth of stabilization. You do it every 50 feet. Do a density test every 50 feet. You do gradation every 50 feet. It's a lime stabilized subgrade, compacted. It's compacted lime stabilized soil. You put your steel in right away. You don't let it dry up. Lime dries up the soil. So if you don't put the steel in and pour concrete right away, you're going to have a bunch of shrinkage cracks in your concrete. So you don't want to have shrinkage cracks. You put the steel in. This is not acceptable. Not acceptable. Not acceptable. You're going to have to remove the steel and relime it and make sure it's wet before you do any kind of a concrete pour. The way you design amount of lime, you can do basically one way is to get enough lime to get your PI less than 20. The better way is use adds a grind method to get a pH of 12.4. This is a pH test. You add lime, you measure the pH of the soil. Once you hit about 12.4, it's about 6%. I usually add 1% lime, so make it 7% for design. So whatever you measure for pH test, you add 1% to it. Or you can use this textile method if you know the PI, and this is percent of the soil binder. You know what that is. You got the PI, you go here and measure the percent lime, 6% here, based on PI of the soil. This is okay. pH method is better. Cement stabilization or fly ash modification. If you have cement, use C150 type 1, mix dry or slurry, apply water, compact near optimum, compact within 2 hours. With lime, you let it sit for 24 to 72 hours to cure. With cement, you got to go in there, add, mix it, and compact within 6 hours. And so, dry method application, this is the cement, you apply it on sandy soils. Only on sandy soils you use cement. So you add water if you need to. Pulverize it. Run gradation on it. Make sure you got proper gradation on your subgrade after they pulverize it. You do the compaction. Got a sheep foot, go back and forth and compacted the cement stabilized soil. You can also do slurry application. You get the cement in the slurry fashion coming in. Again, you pulverize it same way. Compact it. Compact within 2 hours or 6 hours while you're adding the cement. You seal it with a pneumatic. Run density test. Make sure you got proper density. On pavements where you do cement stabilization, that subgrade becomes so hard, you may get what's called reflective cracking in your concrete or asphalt pavements. So you do micro cracking to, crack the pavements. So in this case, use a steel drum roller after you cement stabilization, and you develop small cracks and let it heal. Basically, micro cracking, usually 48 hours after cement stabilization, still vibratory rollers passed over the stabilized subgrade. This will induce micro cracking and relieves tensile stresses. The soil stiffens and recovers. This is called autogenous healing. Will reduce reflective cracking in asphalt pavements. Lime fly ash stabilization, that's another method. If you got sandy soils, you apply the lime, then apply the fly ash. You can do it in one shot. Compact within 2 hours, no more than 6 hours after adding a mixing of the last stabilization agent. You add the lime, let it cure, pulverize it. You bring in the fly ash, the dry fly ash, add water to it, compact within 2 hours. Pulverize it, pack it with a sheep's foot. One density test, make sure the density passes. Construction of the concrete parking lots, compact that soils. Make sure it's nice and compact after stabilization. The typical parking lot. Of course, again, if you got a lime, stabilize it. You bring in the lime, you put it in, pulverize it, add water. Oh, you compact it, set your forms on the stabilized subgrade. You put your steel. Dowel's gonna be all straight, not bent. These are expansion joints. You gotta have chairs everywhere. These are areas that was a little wet. They put lime in it. These are expansion joints. Start pouring concrete. Pouring the finisher. Your slump should not exceed 5 inches. These are the finishers. Bump the concrete here. You use laser guided screed for horizontal concrete placement. It's a laser guided screed. Kind of nice job. Kind of does the whole um, finishing and all that too. Trowel it. Cut the joints 4 to 12 hours. You do the control joints 1/4 of a pavement thickness. You go saw cut it. These are the control joints. You tell the concrete where to crack. These are the control joints. These are the parking lots. Curing compound, after you pour the concrete, you put the membrane on it to let it cure. Doesn't lose all the moisture. If it does, it develops shrinkage cracks. So you go out there and put curing compound on it. You can use burlap. plastic sheeting. Control joints, like I said, with saw cut it. These are the control joints. You can saw cut 1/4 of the thickness of the pavements. It cracks below it, tells you where to crack. Your expansion joints that you're going to have. Typical parking lot, 80 feet apart. For the concrete on both sides of the expansion joints. Same time. Finish it. Run a slump test. Make sure that concrete's got a slump less than 5 inches. This is the cone, 12 inches high. 3 layers in here. You pull the cone up. After you put it in, 3 layers, you rod it at each layer, 25 blows per lift. Pull it up. This is your slump. From here to here is the slump. Should not exceed 5 inches. From here to here. From here to here is 11 inches. This concrete's got too much water in it, you reject it. This concrete here has got a low slump. It's too stiff, you reject it. What does this mean? 5. That means to add 5 gallons of water to your concrete. You never do that on the job site. You don't add water to the concrete. Adding 1 gallon of water to 1 yard of concrete would increase the slump with 1 inch. 1 gallon of water to 1 yard of the concrete would reduce compressor string by 250 psi. 1 gallon of water wastes 25% cement, 25 pounds of cement. 1 gallon of water increases the shrinkage by 10%. 1 gallon of water increases permeability by 50%. 1 gallon of water reduces freeze thaw by 20%. 1 gallon of water reduces salt scaling resistance, increases cracking by 10%, increases the air content, increases segregation. So it's not really worth it. Increase dusting, increases the finishing time. It's not really worth to add it. Making cylinders, we pour the concrete. You got a wheelbarrow, you get the concrete in it. You put it in the 6 by 12 inch concrete cylinders. You rod it 3 layers, 25 blows each layer. Clean the top. Put a cap on it, sit on the job 24 to 48 hours to hardens before you move it to the lab. Then you put it on the back of the truck on cylinder holders so that they don't shake. Otherwise, they lose the strength. You check the temperature of the concrete. It should be somewhere between 75 to 100 degrees. You bring it to the curing room. It's 100% humidity, 72-degree temperature. You break the cylinders at 7 days and 28 days. Typical 3,000 psi concrete. If you need to, you got to core it. Core the concrete, measure the thickness. You break the cores. You got lower strength, for example. You break the cores. So check the core values. If your concrete is average of 3 cores, it's greater than 85%, you're okay. None of the concrete core results should drop below 75% of design strict. So it's a typical 3,000 psi concrete. None of the core compression tests should drop below 2250. Average of 3 cores should not drop below 2550. If they do, your concrete fails. In general, concrete core compression strengths are 15% lower than concrete cylinders because of the curing conditions. Concrete cylinders are in 100% humidity controlled temperatures, and cores are in the field in the hot and cold, so they're not going to cure the same way. Hot weather concreting. If the temperature is high, got a high ambient temperature, high concrete temperature, low relative humidity, high wind, high levels of solar radiation. It's hot and causes reduced water demand, increased rate of slump loss, increased setting time, also workability, plastic shrinkage. Plastic shrinkage appear on surface of the freshly placed concrete. After finishing, they're 1 to 3 feet apart, but 1 to 2 inches deep. They're not structural, but they don't look good. Cold weather, if your temperature is cold, um, you know, if your temperature drops below 40 degrees, you shouldn't pour concrete. If it's more than 50 degrees for half a day, you can pour concrete. If you pour concrete when it's cold, the expansive forces within the concrete result in the disruption of the cement paste matrix. Early freezing can result in a reduction of 50% of the strength of the concrete if it's cold. Concrete should be protected with heaters or blankets until it gets to at least 500 psi. That's usually about 1 to 2 days. Once you hit 500 psi, it can tolerate one freezing cycle. Parking distresses for concrete line. You can see the distress here. See all the distress. Bird bath. A lot of concrete distress areas. Construction of asphalt parking lots. You compact that subgrade, you stabilize it. You bring your gravel, spread it out, compact it with a sheep's foot. 100% modified proctor. Compact it all. Make sure you run density tests. Make sure you got the right density. 100% modified proctor for your gravel material base. If you're going to put asphalt on top of it, you got to put your prime coat on it. Prime coat is a liquid asphalt emulsion aggregate applied to aggregate to prevent graveling and bond the hot mix asphalt to aggregates. Then you put your asphalt in. Got to have that proper temperature. You finish it, you got to compact it. You seal it with a pneumatic roller. Temperature of the concrete is important. Typical concrete, typical asphalt temperature should be between 270 and 325 Fahrenheit degree. If it's really hot and smokes, you got to reject it. If the temperature is too hot for asphalt, it basically lighter fractions of the asphalt will evaporate. This makes the remaining binder stiffer and causes early aging and binder of the binder. The aged binder is more brittle and more susceptible to cracking. Here's a hot, basically asphalt coming in. You got to basically reject it. Temperature, if it's cold, don't put asphalt in. Do not put asphalt less than 2 inches thick when the temperature is, below 50 degrees. And of course, and falling. Asphalt may be placed when the temperature is above 40 and is rising. If the mix is too cold, it stiffens as it cools. This makes it difficult to impossible to proper roadway compaction. The roadway compaction is probably the most important factor in determining longevity of the roadway. Rolling procedure. You got a big parking lot. You use the steel drum roller going back and forth on it. And based on how many passes you get, you're going to get your density that you want. So in this case, you're going to have 4 passes of the steel drum roller to get your density. It's called rolling pattern. That's a steel drum roller going back and forth. Once you do your asphalt, you seal it with a pneumatic, make it look better, provides the contractor with a better surface course, better density. Run the density test on the asphalt, make sure it passes. You core it, make sure you get the proper thickness. It's very important to core the asphalt pavements. A lot of times you don't get the right thickness. So you core it, you get the thickness of it. These are some of the asphalt rocket parking facility near the airport. They didn't put a base in there, they just put the asphalt surface course. The base was very limited. So they developed a bunch of potholes. So you gotta have to have a proper mix temperature, compaction, make sure you got a base. The typical gravel parking lots. You bring in your gravel, compact it over the stabilized subgrade. If it's without geogrid, you bring your gravel, compact it with a sheep's foot. Typical parking lot. Make sure you run density tests, should pass. Compact 100% modified proctor. It's a different typical gravel parking lots. Back to 100% modified proctor. You gravel parking lots with geogrid. That's what we recommend. You go out there and compact that subgrade, proof roll it. You put your geogrid in there. You bring in your gravel, compact to 100% modified proctor. This is the effective geogrid on a pavement. You got a pavement with asphalt, 10 inches of gravel, and subgrade compacted. You're going to have a design value of 117 ESAL. How much basically traffic loading can I have on it? If you want to stabilize it with geogrid, get the maximum life, you put a geogrid on it, you increase your ESAL to 686,000. Really improves the life of the pavements. Minimum construction cost, you reduce the asphalt to 3 inches, your base 7.5 inches. You put the geogrid in here, you're going to have 120,000 ESAL, better than this one. And they cost less than this. For equivalent cost of this, you can have 3 inches of asphalt, 9 inches of base, and geogrid. You're going to have ESAL up to about 349,000. So if you got geogrid, your base thickness is going to be this much. If you don't have a geogrid, you're going to have to use a lot of base. Here's a traffic project. We had a traffic loading of about 0.3 times 10 to the minus 6, 10 to the 6 ESAL. The soil had a CBR of about 4 or 5. Design of 20. If you use gravel without geogrid, you need 14 inches. With geogrid, you only need 8 inches. Here's another one. Traffic loading was 10,000 ESAL. Brazilian modules was 4,500. 4,500. That's like CBR of 3. Real soft soil. Design life of 20 years. Without geogrid, you need 9 inches. With geogrid, you need 6 inches of gravel. Here's another system called TrueGrid. Used all over the place in Houston area and all over Texas. These are cells, basically, plastic cells. That's the grid looking. Use it for parking lots, storage, drive lanes, roadways, fire lanes. That's really good for fire lanes. I was out there in Harris County Precinct 1 building out there near the medical center. I can see the driveway. They got TrueGrid on it. But it looks like the cells full of gravel. This is a Pro Plus used for heavy loads. Max for real heavy loads. And typical designs. Now this thing has of course this is heavy loads again. Fire trucks. Tool grid is used to drive on and drain and detain the storm water below. It's got a void space of about 40%. This is 0.4 cubic feet of storage area for each cubic foot of the aggregate. So you can use it as a detention. So it's a typical for heavy truck loading. Your true grid is about 1.5 inches. Below that, you got 8 inches of gravel with void space of 0.4. Here's another one. You got that. The true grid. Below that, it could be depending on what the thickness you want it to be. You got a pipe drain at the bottom of it too. You got the fabric. Gravel parking lot distress. We see a lot of that. This one here, they had no stabilization, nothing. They just put gravel and drove trucks on top of it, and it failed. Perch water table again. You got parts of Houston where you got perch water table. You got that sandy soils over clay. Water sits over here. Regular water table could be 20 feet. Perch water table could be about 1 foot. You take out the trees. That's what the ground looks like. You can't put a parking lot on it. Water just sits there on top of the clays. The perch water table conditions. As sandy soils that got in Katy. You go out there along 249, 290 area, cypress wood, woodlands. So in this case, you got to stabilize that soil before you put a parking lot on it. So the way you improve the pumping, of course, by scarify, open it up, let it dry up, improve the drainage. You can do soil mixing, you can do chemical modification, you can do removal and replacement. Open it up. It doesn't make sense to open it up because we got lots of rain in the Houston area. Every time you open it up, it's going to rain, so it's not going to dry up. So that's not a good option. You can do drainage if you got a big parking lot, not a small one. You get that and you put bleeder ditches in it, about 3 foot wide, 3 feet deep. You drain the sand and silt. You take it to like a detention pond. You pump it out. You can mix the sand with clays. So if you got a project, you got a detention pond where you got clay in it, you can get some of that clay from the detention pond or channels that you do and bring it in and disc it in into the sand on the surface. And then it won't pump anymore. You do chemical stabilization. You can use fly ash or lime. This is fly ash. You can put it in. You can use quicklime. This is the best one. Do not use lime slurry. Removal and replacement. Expensive. You cannot remove the sand and stuff. Bring in a structural fill and compact it. Detention ponds under parking lots. Because of the land use nowadays, they're putting a lot of detention ponds under the parking lots because they don't have enough space for the detention ponds. So they put these rubber plastic stuff in here, like they put gravel on top of it, and you got a fabric underneath it. So you go in there and make sure the ground is nice and hard. You got a good bearing capacity. You put in your fabric. You put your detention system in there. There's like pipes. And you fill it up with gravel in here. You put concrete on top of it. You can have concrete systems. You can have these plastic systems, like boxes that sit on top of each other. You put your fabric in, of course, you put these boxes on top of it. Then you're gonna have paving on top of that. That'll be your storage underneath it. All that gravel and all that should be compact to 100% modified Proctor. You're gonna have light poles in your parking areas. You got to provide isolation joints between your pavements and your light poles so that if the pavement moves up and down, it's not going to move your light poles, or if your light pole moves, you don't need, of course, any joint between the asphalt and light poles. That's it. Pictures. If you got pictures of the parking lots cracking up and stuff, send me some pictures. I would appreciate good pictures. This program is going to be on YouTube. You got to go to the Geotech Engineering Testing YouTube channel to watch it. We got a poll, see how you like the program. If you want to add something, email me what your suggestions are. Add me pictures, send me pictures of the stuff. That helps me, kind of explain stuff. Um, you can contact me at geotechde at geotecheng.com. My number is 713-699-4000. We're going to have a bunch of webinars coming up. Just keep tuned to what's coming up. You're going to get a PDH within a week or so for 1.5 hours on this thing. It's important to do a proper geotechnical report on your parking lot or any building you're going to have. Otherwise, you're going to get this change order. So it costs a lot of money to go fix stuff. Questions?